Some quick announcement. Okay, I'll make them official on the Moodle announcement today. So, several things. Let's make it consistent. So all the quizzes will be on Wednesday, given that we started our first quiz on Wednesday. So your next quiz will be next Wednesday. Okay, and then it's going to cover everything. I'll specify the range tonight or tomorrow, but until what we are going to cover today. Okay. And then office hour, I'll also announce that the extra ones. But for this Friday, if you need to see me for questions, feel free to come 2:30 p.m. this Friday. Okay, feel free. And then for your quiz number 1, I will try to make it available for you to pick up on this Friday. I'll announce that. If I really cannot make it, I'll definitely make sure it's Monday. Okay, at least before quiz number 2, you can see it. Okay. Okay, so let's go on to our example. Okay. Let's start with this guy here. Oh, just to remind you, the kind of question you want to get comfortable with is a simple one. That's something I left as an exercise for you. Given, yeah?
Even if you can't make it Friday, you'll bring it to class on Monday.
The quizzes, yes. So if I really, even if I could make it available on Friday, let's say, whoever couldn't really come, I will bring the paper to Monday so you can still pick it up. That's not a problem, yes. Okay, so for this kind of exercise, if you're given a grammar like this, I might just ask you, is the following context-free grammar ambiguous? And again, for you, you just want to somehow come up with some string, which you will demonstrate. If you want to show it's ambiguous, you want to show it has either distinct parse trees or have distinct leftmost derivations or have distinct rightmost derivations, right? That's what we said last time. Let's do a slightly more complicated example, okay? This one, I'll leave that to you as an exercise. Let me go back to the slides and talk about it. Okay, now, let's think about this grammar. This has to do with what we said as dangling else. Dangling else is actually quite a famous problem when you talk about context-free grammar. Okay, look at this grammar here, okay? Think about it, and would you think this grammar is okay? When I say ... over there, I simply meant there might be something more, but you don't need to know it in order for this example. Let me just go through that with you a little bit. We're saying that we got programming statements which produces either one of the 3 possibilities. It could be an assignment at the end, or it could be if-then without the else, or it could be if-then with the else. And then, of course, it's recursive. That's the nature of CFG. If you got answer, just hold it, just for now, okay? But think about it. If you got questions, go ahead. I just want everybody to think, yeah. Oh, you got some answer, just hold it. Yeah, let's wait a little bit, okay? Okay, at least everybody can look at that and have some thought. If you have no clue, that's okay. At least you can struggle a little bit with this. This is kind of the simple grammar, the situation we want to get used to. Okay, any thoughts? Would you think that's ambiguous, or you don't think that's ambiguous? I heard probably yes. Okay, Coco, do you want to say something?
So you can match the first if statement with the first, and then if else afterwards with the second, or you can match the if else, but the statement will create another if statement.
Okay, basically, you're basically saying it's possible to find a string such that you can have 2 different parse trees. Is that what you're suggesting? Okay, so now I agree with you. Can you tell me what that string might be? Okay, I'll do it. Okay, first of all, let's see if that's the one I want to talk about. That's okay. We may have more example. If something, right? Let me just say expression 1, some expression. Okay, if, then statements. But statement is recursive, so you cannot just put statement here. Oh, if then. If then, and then, before that, of course, after this if, it should be maybe expression 2, okay? And then? Maybe something, right? Oh no, this should be a statement over here. So after the then, it should be another statement. Can it be assignments, maybe? Assignment 1, and then else? Assignment, okay, that's good. This is exactly what I wanted to talk about. That's good. Okay. So guys, I would suggest take take a look at this string over here. For those of you who arrived a little bit late, that's okay. Let me bring you up to speed. I presented this particular question over here just for everybody quickly. Okay, look at this particular grammar here. The question is this grammar ambiguous? Okay, you can think about think a little bit more to yourself. It turns out it is. And what Coco just suggested was a string. Let me put it in this form. Okay, the same. Okay. Now take a look at this string over here. How many possible parse trees can you actually generate from this? How many? Is it if there's only a unique string? If there's only a unique parse tree for this particular string, then it cannot be used as a witness for proving that it's ambiguous. Of course, Chelsea. Take a look. That's fine. I think that's an important step. Miska.
Is it a problem because it's recursive?
Yes, no problem here. Okay. This particular string is not recursive, right? You can think about, I'm just saying some expression 1, because I don't really have the detail for how expression might be. That's just some expression. Assuming that expression 1 is already some expression, concrete one. And then also assignment 1 is simply some variable assigned. Maybe x is assigned to 3, and assignment 2, maybe x is assigned to 4, something like that.
Well, because you have two statements in the if expression there.
Which one? You mean the second rule or the first rule?
The second rule means you can have two branches right there.
Can you make it a little bit more clearer? What do you mean?
This, it doesn't have to be simultaneous. Again.
Well, no. First of all, would you agree? This is a valid string according to the grammar.
Yes.
Okay, so now, number 1, this is a valid string. Number 2, if this is a valid string, is there a unique parse tree for this string? That's the second question. If you say yes, then this cannot be a witness for proving that the grammar is ambiguous. If your answer is no, we do have 2 distinct parse trees. In that case, this can be used as a witness, right? Let's get it clear. Chelsea.
Does it depend, I don't know if this is right, but like, could the else be associated with the first two statements?
Okay, you're basically, Chelsea, basically posing a question. Should the assignment over here, for example, should the else over here, let's say the else over here, should it belong to the first if, or should it belong to the second if?
Yeah, because then it could be like, if expression 1, then it goes to the expression 2, but the else is either associated with the outside one or the inside one.
Okay, yeah, go ahead.
So you can do if expression, then statement, else statement. You replace the first statement in there, and you just and then second statement with the sign.
Okay,
Yes.
good. Anyway, so at least everybody got a chance to think about it. Basically, you're on the right track. Okay, we just need to write it down precisely for everybody. Okay, good, no problem. So basically, let's talk about this particular guy here. So it turns out there are 2 different ways to parse the string. Okay, either you can say, I can say here, if expression 1, then in that case, this guy over here simply just belongs to the body of the then, right? That's one way to parse it. Okay. Another way to do it would be to say, if I can somehow go over all, you know what? It's easier for me to show you a tree. Okay, how about we show the tree right away? Sorry, it's a little bit harder for me to annotate. Let me take a look at the tree over here. Okay. So now, this is one of the possibilities. Okay. This one is saying the following. Let's just convince ourselves. So I don't need to build from scratch. Okay. So I got 2 parse trees for you. I just convince ourselves both are valid, but they're different. Okay. So now, if you look at the first one here, we start with statements, and then we say if, and then we got expression 1, okay, and then we got then, and now we got statements, and then we got else, and then we got statements, right? This is valid. And then somehow we want this particular guy. Let me highlight it for you. We want this, the one I just highlighted, that one there, to belong to the true branch for the expression 1. Can you see it? Okay. So now, which means under this particular statements, I want to show that eventually I can get to if, then, and then assignment 1, basically. That's one way to interpret that for the parse tree. And then in that case, what about assignment 2? For assignment 2, it simply belong to basically outer if for the first parse tree. Is everybody okay? For the let me just make a conclusion here. For the first way to parse it, basically we're saying that for assignment number 2 belongs to the outer if over here. If, then else, and then you got assignment 2. That's one way to understand it. So what you should do when you study is to convince yourself, number 1, this is a parse tree. And once you have convinced yourself, you will see that assignment number 2 basically belong to the statements of the else of the outer if. Okay, that's number 1. Any questions for this one here?
For the first one, Parse Tree, the second one, the case expression that
So, okay. Are you okay with this particular one, first of all? So this is the first derivation we do. You okay with that one?
yeah, which one is that?
That one is here. We're saying statement, okay, first of all, we say statements produces this guy here. We're using this production. Oh, maybe I should have said that, right? Okay, good. And then we simply got that. Okay, that's one way to parse it. So now for the first one here, assignment 2 belongs to the outer if. There's another way to parse it, but assignment 2 belongs to a different way. So that has a different meaning. Okay? Let's look at the second way to parse it. Okay? The second way here is also valid. Okay? Let's see how we can do it. Okay, let me annotate a little bit better. So here we're saying statements, that's how we started with. And then we chose, rather than the second rule first, we chose the first rule first. And we chose this guy here. We only got if, then. Okay, so that's why we got if, then, expression 1. Okay, so now for this particular statement over here, okay, so now here's a statement. And for that one, we actually try to apply rule number 2. You can see the order in which we apply the rule. For the previous one is, if you think about this is 1, this is 2. In the previous parse tree, we do 2 first and then 1. But now we do 1 first and then 2. Okay, if you think it that way. Okay, so now for statement over here, you can see if, then, else. Right? So if, then, else is number 2 here. And then you can see assignment 2 now belongs to this particular if statements, which is, let me highlight it. So if this is the if statement over here, you can see this assignment 2 belongs to this particular if. Let me just make it, maybe you need some indentation. If I put it here, if, so this is similar to what I said on Monday. Okay, let me just put it in that form. And then we have if expression 2. And then assignment 1. Otherwise, assignment 2. Okay, that's kind of the input. Okay, think about that as input. And I'm going to make it 2 copies and show you how they are going to be different. Apparently, for the same input string, there are 2 different ways to interpret that, given the grammar, which means the grammar is not good, it's ambiguous. Okay? The first way is to say if, then, and then else, assignment 2. And then this particular guy is simply just belong to the if branch. That's one way to see it. Okay? And the second one over there is like this. We say that if, then, and then this part over here is a body of the if. And that part there actually contains the if and also else. So there are 2 different ways to interpret that. Definitely not a good thing. Okay?
In Java?
Well, actually, I tell you what, this one you can see you will have similar situation in Java as well. So you have to know which one you'll be taken.
In Java, can't we just like put the else inside the?
You may, of course, you may put brackets to actually force the. But how about this? That's why I asked the other day whether anybody took a 1022 with me. I'll just, let me try to recall, if I can recall the example, okay? In Java, for example.
Yeah, in Java, one line there statements don't need the reference,
Yes.
but it would still understand it.
For example, over here, okay, let's say here we'll simply say print 2 over here. Otherwise, we say print 3, right? It's a similar situation, right? Basically, in Java, if the body of your branching or the loop only got one line, you don't need the brackets. So let's say you have this situation over here, right? So now you have to know which if does it belong to. Rahul, you see my point here? Okay. Anyway, just for your information, Java takes the following interpretation. It belongs to the nearest if. Okay? Anyway, that's something for your information. For Java, for its grammar, it actually does something which will make sure it select this particular interpretation. So there's no ambiguity. Okay? So let's go back to this. Okay? Guys, any question about this? What should you learn from this particular example? I'm just saying, showing you some programming language example here. Given the grammar, you should really somehow try to come up with a string that will prove that it's ambiguous, if you can. If you cannot, it better be unambiguous. Right? Okay, how can we fix this? I'll give you a solution and then try to walk with you a little bit, just give you some intuition. How can we change the grammar so that it becomes unambiguous? Let me just go back to the clean version over here. Apparently this is ambiguous, right? How can we change it? Go ahead. You may want to, well, there's no multiplication here. Let's say we still just want to talk about if then. We want to allow if then, we want to allow if then else, also we want to allow assignment. Don't worry about the multiplication or addition. It's going to add complication to our discussion. You mean by adding some variable? How? Well, oh yeah, it's okay. You know, you're just saying, suggesting maybe you should add more variable. For that one, I agree with you. That's on the right track.
Well, one other, like I know Java doesn't do this, but you could enforce some kind of delimiters, like between the then and the else and after the else. Like have
You mean have some like a bracket or something? Let's say we don't do that. That could work, but that's not. How about this? I kind of follow what the textbook suggested, which is nice. Let's say we don't add any extra delimiters for that. Let's say we don't.
well, I would say
Add which is a variable. Again, how? Yeah. No, on a good track, which is good. Miss Guff?
Well, you can have just different variable for two statements. It's still a statement.
Ah, are you talking? Okay,
One is statement.
it's a little bit better. Okay, so are you talking about this particular line?
Yeah.
That's exactly the key of the problem. The key problem is, if you look at the production rule number 2, okay? If you look at the rule where we say if expression, then we do statements, which means this part for the true branch may be substituted by using whatever statement is defined. Else part is the same. That means we allow some circularity over here, right? We might use 2-1 and 1-2, right? So that's why the ambiguity comes from. When you see the solution, that's exactly solving this problem. Number 1 is going to add an extra variable for sure. But number 2, where exactly does it add? That's something we're going to see as a case study. Yes?
You have to force that the second statement has to look like if else statement.
Yeah, somehow you don't really want to limit the set of string that can be accepted by the grammar. So what you want to do is, for example, what you will see in the solution is to say somehow we want to say we can choose either one. Either this one shouldn't be called statement anymore, or the second occurrence shouldn't be called statement anymore. We want to create some extra variable. For example, let's say statement 2. Let's say if we create another variable called statement 2 and then define statement 2 elsewhere and make sure statement 2 doesn't come back to a statement. So they are completely independent. That's kind of intuition. Okay? Let's take a look and then just convince ourselves. Okay, so these are the 2 parse trees. Okay, make sure you can draw them without any problem. Okay. Oh, it's called dangling else problem. Okay, it's again, it dates back to Algo 60, well, a long time ago. Okay, just for historical reason. And you may actually want to practice yourself how to show the leftmost derivations for these two parse trees. That might be a good exercise. Maybe leftmost and rightmost. Okay, give it a try. Okay, let's see how we can solve it. Oh, so these are just the two meanings I talked about before. Okay, so this part you can just look at that. So now, how do we solve it? Let's look at the grammar. So the first part we say statement produces if expression then statement. That part is the same. But now, back to you guys, good idea. We say if expression then like a statement 2, let's say with else. Otherwise, the same statement. Which means if you think about we're drawing a graph, statement will just go back to itself. And with else will go to another variable. You want to make sure that variable doesn't come back to statements. There's no circularity. Okay, assignment is the more like a base case. With else, it's just another variable we introduce, like that. Okay, I believe that's the whole grammar.
Again, isn't it forcing to have an else would be first?
Nope, not quite. Not quite. Some, yeah, Chelsea, go ahead first.
So this is like what you were saying in Java, where it's always associated with an else.
I'm not sure if Java defined the grammar exactly like this. I'm just saying maybe Java does something similar to this.
The idea that you were saying that the way Java is that intuitively an else associated with
Or let me make it clear. Okay, sorry for interrupting you. So let's see this. The grammar you just saw is a solution. It's going to make sure if you got things like this, for example, right? It's going to make sure always you will choose the closest if. It's going to make sure, but we're going to see one example to see why.
Can I give you an example of why it works? So go
You-
back to your.
You want one example? It works or doesn't work?
It doesn't work.
Okay, okay, tell me the example. Yes, I do have on my iPad. Give me just one moment. Okay.
So if
Yeah, sorry. Let me just get that. Oh, sorry. This guy here. Let me just copy that. So that's actually the new grammar. Okay, first of all, this is a grammar that I'm proposing to you, right? So from the textbook. Okay, you are saying that you want to have one string which you believe is not going to be accepted by this grammar. Am I right?
yeah,
Okay, go ahead. Huh?
never mind.
Never mind. Okay. What did you think? What was in your mind, please?
It was if that
Go ahead. I'm gonna write it down. If
if
some expression, let's say expression 1,
expression one,
then
if expression two,
expression 2, then some assignment, I suppose.
yes. Else,
Oh, actually, this is the same string, right?
yeah.
Okay.
Assignment,
And they want to have another if?
yeah. If assignment two.
No, you cannot say, if you say if assignment, no, it's not possible. Because after if, it must be an expression. Of course, it's not
I
possible.
mean, if expression then.
Okay, I can do that. If, and then you would say expression
Expression
3, and then
assignment two.
assignment 2. Interesting. Is that possible? Okay. Why don't we try? Okay, since Coco actually got a very quick response, that's good. Okay. How about we do this example all together to convince you? Okay, you will see another example in the slide. You can do both. Okay. So now let's say this. Can I just be a little bit lazy? I'll say this is simply S, and this is let's say with else. I'll say WE. Okay. So now you and then I will call this expression here. I'll call it E. Okay. And then anything else I didn't rename? Okay, that's fine. So let's say I start with S over here. this will be relevant to what you're going to see next. Because you can see the way we are trying to do derivation right now is completely manual. We're going to see exactly how we can automate this particular this complete process to do parsing. Okay, we're gonna get there. Okay, let's do this example here. Coco, be our guest. S, I should, okay, you say if, and then, yes, let's try that. And then I would say statements. Okay, of course, this will go to expression 1, right? Okay, very good. And then for statement over here, it's going to be go again.
Expression, then without statement. Now expression goes to expression. And statement goes to everything.
Okay, how about after then? After here, what would that be? With else or the first one?
Without.
Let's try. With else, and then with else, and then of course, after with else, we also got else, and then we also got statement here, right?
Yeah. And else goes to assignment 1.
Assignment 1.
Last statement goes to expression, then statement.
Wow. If statement here, let me just use a different color. And then over here, I would say if the first one, right? Expression, and then, okay, statements, of course, that one can go to assignment. Yeah, thank you. Assignment 2, and then this will be expression 3. Okay, so now you should have a look at the leaf. If expression 1, then if expression 2, then assignment 1, else if expression 3, then assignment 2. Perfect. Perfect. Thank you. That's very good. Impressive. Good. Guys, are we okay with this? So now, for this particular exercise, I would say if you never saw this problem before and they ask you this, it would be a challenging one. Of course, you would take some time to think about it. But now, since I got a solution available, that's why I present to you. Again, the pattern would be I gave you a particular grammar. You want to try very hard to think about if you can find any witness string. Usually, that's really too hard. I'll give you a little bit hints in the exam or in the test. Okay? But once you come up with the string, if the grammar you believe is ambiguous, you're going to show at least 2 parse trees, right? Otherwise, you can show other cases. Okay. Any question about this particular example? Everybody happy? Okay. All right. Okay, I got a little bit of explanation over here why this particular original grammar is actually ambiguous, because we're mixing the category, right? Because you have basically that statement and statement in the previous one, okay? But now we are basically improving it. So when you go to the true branch, this should be false, sorry. If you go to true branch, you will go to with else. If you go to false branch, you will go to statement, right? There are different branches, different variables. I'll change the typo there. It's a typo, of course. No circularity. Okay, any question about this example here? Everybody okay? Okay. I think up to now, we basically were trying to review what you learned back in 2001, maybe with some example you haven't seen before. But so far, all the process we're undergoing is basically manual, right? We don't actually talk about is it possible to encode the process of doing, for example, leftmost derivation. Is it possible to automate the process? That's something we want to learn, okay? Let's see. Let me give you a little bit of context in the next slide, and then we'll see some algorithm. Let's say you're given a grammar. Okay, again, every grammar has variables, has alphabets, has production rules, has star symbol. And given some particular input program, and of course there should be no variables in the input stream, right? Everything should be alphabet, composition of the alphabets. So far, we manually try to come up with a derivation, if we could, right? Now, a parser is what we want to do in this course. And of course, eventually, when you do your project later, you don't really have to implement the parser yourself because it can generate the parser automatically for you. Okay? But at least we should understand the underlying theory. That's something we should really do. Okay, the parser is going to automate this derivation process. Okay, I'm going to describe that intuitively to you. Basically, given an input sequence, remember this is not a second phase for the compiler. In the first phase, we got scanner, in which case all the misspelled words have been filtered out already. So now we got a sequence of tokens with their syntactic categories. So remember the example we did about register, right? So now you have to say either there is a valid, maybe leftmost derivation for the input string, or you say error. There's a grammatical error for your input string, right? That's kind of the outcomes. Of course, it should be a decidable process. Otherwise, we cannot encode it. Okay, so now in the process over here, okay, think about the abstract syntax tree. Okay, just give me one moment. I'm just going to put something on the iPad, give you a little bit idea, abstractly, before we see the code. Okay, so now for the abstract syntax tree, let's think about over here. If I got A plus A multiplied by A, right? That's something we have seen a lot. Eventually, we want to build an abstract syntax tree, something like this, like a tree, right? Doesn't have to be this shape, just in general, okay, like a tree. Question 1, what should be the root of the tree? Is it always the case? Exactly, the start variable. Exactly, that's exactly the answer, okay? This is always the start variable. So this is something that's always true. That means our algorithm later is going to start from this point, okay? Start variable. And some stuff in the middle, what about the leaves for the tree? Huh? Terminals, I agree. Basically, okay, we'll put it in this way. Would you agree? Somehow the leaves are going to contain A, contain plus, contain A, right? Agree? But in what order? Basically, you should follow exactly the same order as how the input sequence was entered, right? For example, just to bring to your attention, from this one here, if you look at the leaf, if expression 1, then if, etc. You follow exactly this particular order of the input sequence, right? Something to note, okay? So we also know for this particular parse tree, when we talk about the leaves, it's going to be somehow A plus A multiplied by A, somehow. And we know the top level, we also know the bottom level. So now the problem is, how do we figure out how do they connect together? Internal nodes, that's our job. Internal nodes. What will be the internal nodes in this case? Yeah, or any variable here can be internal nodes, right? Okay, good, that's what you meant. Anyway, that's something I want you to have in mind first, okay? Eventually, we're going to build a parse tree out of any grammar. The root is always the start symbol. The leaves will be also the input token sequence. And whatever that's in between has to follow some production rule, of course, or all of them. And then every internal node will just be a variable. Okay, that's a principle. Okay, if everybody's okay, let me go ahead. The root, the internal nodes, and leaves, and etc. So now, how do we discover the grammatical connections between them according to the production rule? That's the tricky part. So there are two approaches to do parsing. Okay, I actually gave you intuition sentence over here for the first and second. The first one is actually called the top-down parsing. Okay, that's something we're going to introduce you today. Okay, another one is called bottom-up. Basically, different approaches. Okay, let's just talk about top-down quickly. Okay, and maybe as soon as I try to I'll write something down in the iPad and then I'll switch. Maybe as soon as after I describe roughly how it might work, you might find some similarity to something you have done before. You may. Okay, just bear with me. A, B, okay, let's go back here. Yes, you may. Go ahead.
Is this the one that they talk about like LL versus going parsing the like different compiler types? One does LL, which is
Not quite. That's something we'll get into. So here we talk about even higher level. We only talk about either top down or bottom up. Okay. Yeah. So now let's see. We got the grammar, right? Okay. So now let's say this. Let's say for our grammar, okay, let's say in your grammar, somewhere you actually got a production. A produces W somehow, okay? And then let's say we already got our star symbol over here. And then we have constructed a tree somehow. This is already partially completed. Let's say we have an internal node that represents A. So now, one way to try is maybe we can try to produce a subtree that kind of corresponds to W. If this is possible. If that's possible, then we are fine. If not possible, maybe the fact that we have chosen A over here is actually wrong, that we may have to go back to some previous step and try to reconstruct the tree. So like a backtrack kind of process. Have you done something similar before? No? Are you sure? Let me remind you, 3101. In 3101, is there an algorithm? What? Not dynamic programming. Dynamic programming uses a matrix, right? But okay, in 3101, you somehow start from somewhere. You want to do some traversal. You want to make sure every time you go somewhere, you want to make sure that's somewhere you haven't really visited before. Depth first search. Similar, not exactly the same. Okay, so it might be worth for you to review a little bit depth first search as a comparison. Okay, but for now, we just talk about the top-down parsing. You can think about the way I'm going to describe the program very soon. Okay, we are going to maintain a stack in our program, a stack. That's why it's similar to depth first search. And then we're going to gradually put the node that has to be built later. So put it in track. Okay? And then every time when we are done with a particular tree, we'll simply get rid of this, pop it off. If eventually we are so smooth, and then we can go all the way to the end, and then we are done. Right? That's kind of the process. Of course, when you really trace the code, it's a little bit tedious. But let's see the algorithm first. Okay? Let's take a look. Okay, another one is called bottom up. We'll get there maybe when we get there. Okay, we don't need to talk about it today. Oh, did I? Oh, that's the algorithm. You know what? For some reason, I got this slide in the wrong place. I'll fix that. Okay, this slide should not be there. Okay, sorry about that. Let's go to the algorithm directly. Is it even visible for you at the back? Is it okay? Okay, I'll just go line by line first to give you some intuition, and then we have to trace it a little bit. Okay, it's quite interesting. Okay, the algorithm I just call it TD parse, top-down parsing. Okay, the input is just going to be some grammar, and then also some input string. You're going to read in one word or one token at a time. Okay, the output is going to be two kinds. Either the input program or input string will be accepted. You just return the root of the parse tree. That means you can build a tree. Otherwise, you just report to say you got syntax error. Okay, either one. Okay, it's decidable. It will always give you an answer. Now, for the procedure over here, the first step, you have to somehow maintain the root. Okay, you see how we start with. Whatever the star symbol might be for your grammar, create a tree node for that, and then make it a root of your parse tree. Okay, that's easy. And then focus simply means what node should we focus on constructing at the moment. Okay, of course we'll start from the root. That's why it's called top down. And then we initialize an empty stack. Let me call it trace. It's more like a trace of our derivation or our production. And then the text will simply say trace.push null. Okay, that's just one way to think of it. Because eventually, when you are done with all your input tokens, and then your stack only has null remaining, that means you're successful. Okay, just one way to think of it. If later on, if you ever have to implement the parser yourself for whatever reason, in that case, you can feel free to adapt this to your own coding. That's fine. We just talk about the abstract idea. Okay, and then we talk about the word. The word is basically whatever token we have to handle at the moment, right? From left to right in the input token sequence. Okay, so now this is an interesting bit. While true, right? Maybe your 1022 instructor told you while true, it may not be so good. It may never terminate, right? It's not guaranteed, right? It may terminate, but it may not. But just how the textbook presented it. By the way, I fixed some details in the algorithm, so hopefully that's easier for you to comprehend. Anyway, somehow inside the body of the while loop, we're going to return for different reasons. Either we found an error, so we return. Or we finish processing the input, so now we can return the root of the parse tree. Okay? For each of the iteration, we got different cases. It's going to be a long if-then-else statements. We're saying the following. Okay, let me see if I can try to draw some diagram at the meanwhile. Okay. Okay. Take a look at this to see how you understand it, and then I'm going to draw something on the diagram. Try to read it this way. Focus over here, think about it's more like a variable. Okay, somehow the textbook present the algorithm in a way that may not be exactly type correct, so we can tolerate this a little bit. Okay, think about focus tells you tell you about a node of some non-terminal, the internal node. Okay, if it is actually a variable in your grammar, so now you want to see whether you have already visited that rule. That means that's why I put unvisited. Okay? If everything for this particular focus variable has been visited, that means we have exhausted all the possibilities. Right? In that case, we may have to either backtrack or we say, oh, we're done. There's an input error. Okay? So now what we are doing over here is like this. Imagine that we start our parse tree with the start symbol over here. And then let's say somewhere in the middle, this is the focus right now. Okay, so this is a node we want to build a tree. Let's say in your grammar, okay, you actually got focus, just a variable, right? Somehow can produce some right-hand side, basically. Okay, the right-hand side might contain different components, right? Can be terminal, can be non-terminal. So we just call it alpha. Okay, we say alpha 1, alpha 2, alpha 3, etc., alpha n. So the way we do it is by saying, now we want to grow the tree a little bit by saying alpha 1, there should be a node. Alpha 2, there should be a node all the way to alpha n. We create n nodes over here. Okay? And then we also have to maintain a stack somehow. And then we want to make sure we push the stuff into it. So now we want to make sure we do the leftmost derivation. In that case, we should really say alpha n minus 1, all the way to alpha 2. And now we can now focus on this, alpha 1. So more like a leftmost derivation. Question here.
How do you code comparison to variable if you have some kinds?
Imagine that maybe somehow you have a class called CFG, for example. And then in the CFG, you may have a hash map, let's say. And the hash map has a key being string variables from the non-terminal. It might map to certain array list, which will be a list of maybe terminals and non-terminals. That's more like implementation details. Yeah. Okay, that's about this particular one. And then the next line will be, and then we simply create a nodes and as children, and then we push to the stack, and then we switch the focus, right? That's something I just mentioned. Otherwise, so that means we have to distinguish between two cases. If somehow there's no unvisited node, if there's no unvisited rule for me to use, in that case, I have to basically check to see if, let's say this, in the worst case, if I'm currently focusing on this particular rule, the start symbol, but somehow I have already exhausted all the possible productions for S, but nothing works to match the current input. That means it should be an error. On the other hand, if somehow I'm actually in the middle of the tree, if nothing actually works for this particular focus, what I should do is maybe I should go back to its parents and try different rule from there. So hopefully this sounds more like a depth first search for you. That's why I said you may want to review depth first search a little bit. Okay, that will help you. Okay. Okay, and then after that, okay, that's about this particular branch. So now this is the good case. This is saying if the current word matches the focus, like a terminal. So that means we're good. We can move on. Okay. The way to move on is we simply say we read the next word and then change the focus to the next one. Right? Remember the stack actually keep track of the order of visiting the nodes, okay, in a leftmost fashion. Okay. Okay. Now this is actually funny. So the else if over here is saying that if the word is EOF, meaning that we are at the end of the input, no more, and then the focus will just be null, meaning that. Yeah, think about, well, remember I said the stack, they put the first one is called null. That means the stack is empty, nothing to move further, also input is done, so we are done. Okay, that's the good case, you hope. Okay, finally, this simply, this else part simply means if currently the word we are reading is simply not good for now, then we may have a chance to backtrack. Okay, that's a little bit of detail here. And for the backtrack, also define them over here simply means you gotta pop off the stack, change the focus to parents, and also reset the children. We're gonna see that. Okay, so that will be the complete algorithm. Okay, wow, good. Any conceptual question? We're gonna do a little bit tracing. Yes, question, please. Oh, reset children. Okay, easy. Okay, I'm glad you have some question. That's good. Sometimes if you have no question, I'm worried. Right? Reset children goes like this. Okay, for example, let's say if I'm currently in the focus over here, for example, okay, if I already got certain nodes over here, let's say I'll just put it here. Let's say focus can produce 3 children over here. So now, if I find that this particular tree is not going to match my input sequence for some reason, so now what I want to do is go to the parents of the focus over there and backtrack. When I go backtrack, I'm going to set this to be the new focus. In that case, what I should do is I should simply just reset this tree. Yeah, simply delete it. So that means I can start from scratch from its parents. That's a backtrack process. Yeah, I'm glad you asked. Guys, any conceptual question? We're going to trace the code, don't worry. Right? I thought it might be worth asking you about it. Chelsea, any conceptual question for me? Yeah, so I tell you what, this one here, as you see by me tracing the code, this one is not 100% precise, but we'll see, right? Let me just go back to there. You're talking about this particular line over here, correct? That one there basically is saying, how can I expand the current node further? Okay, let me refer you to this particular slide, okay? But I think I better give you intuition first. If I'm currently in focus over here, somewhere in the tree, I should really keep expanding the tree. How can I expand it? I should really try to see if maybe focus is simply, for example, EXPR, for example, in our grammar. I'll try to look at EXPR in my grammar over here. There might be possibility 1, possibility number 2. Maybe I previously tried this possibility already, but it didn't work out, so that's why I backtrack. And now I can try this one here again to grow the tree. That's somehow, yes, yeah. So that's why I said, again, you may want to revisit the depth first search a little bit. That will help. Mm-hmm. Okay, good. Having said this, we should do example. Otherwise, it's not very good if I just give this to you and say, understand it, right? That's not good. Okay. Let's do some example. Let's say the first example here. Okay, let's do something simple. Even for something simple, you can give very good insight. Okay. You're familiar with this grammar, okay, no problem, okay? Now, we want to trace to see how we can build an abstract syntax tree from this string over here. You know how to do it manually, okay? So here's my question for everybody, okay? First of all, I'll give you 30 seconds to think about it, and there's a reason for that. Let me switch to my iPad and give you everything. Okay, let me present my question to you, and I'll give you 30 seconds to think about. Okay, This is exactly the same algorithm I just presented to you. Okay, this is the grammar that we previously did together. That's recursive for short. And now let's say we want to parse this particular string, which we drew manually previously. Right? Now, can you imagine the process of building a abstract syntax tree out of this string? Think about it for 30 seconds. If you have an answer, hold it, please. Try to run it a little bit in your mind. Try it. If at least you try, I'll be very happy, right? Yeah. Okay. Anyone got anything to say before I start tracing it? Ashkan, anything to say? You thought somehow it might just work, right? You would think. Good. Oh yeah, I'll trade. Don't worry. So my question is, do you see any immediate concern from your side? Do you understand what the problem is?
Yeah, the ambiguity here, we're going to have a situation where we'll be able to match it.
What do you mean ambiguity? Sorry.
Well, this grammar was ambiguous, and then we're going to have an issue.
Oh, actually, this one is not ambiguous. Yeah, remember we introduced a level. Yeah. Okay, the grammar is not ambiguous, and the string is definitely going to have a parse tree as we manually prove. So now we're going to run the algorithm. Okay, guys? Wow, I'm happy. Nobody saw the error. There's an error here. Should I give you another? Okay, I really don't want to tell you the answer right away. You lose the learning opportunity. Okay, how about I'll let you try one more. If nothing wrong with the algorithm, nothing wrong with the grammar, it's unambiguous. If I run this algorithm on this input string with respect to this grammar, what's going to happen? Am I going to get a parse tree or not? Or is it going to tell me syntax error or something else?
We'll just return you the root, which I'm assuming is just expression.
Well, before I try tracing, I want you to think a little bit in your mind. Okay? It will definitely make everything concrete to you. Ooh, you think you will turn into an infinite loop? Why would you think so?
Because from factor can go to expression, and then from expression can go to expression, factor, expression.
Aha. Okay, Coco, that's very nice. Okay, let me just tell you a conclusion first of all. What we're going to do it to really convince you. Okay, this particular grammar, nothing wrong with it. However, what's wrong is you're trying to apply the top-down parsing algorithm on this grammar. The grammar is so-called left-recursive. Did you hear about this term maybe back in 2001, maybe? Or 2000, okay, if no, that's fine. Huh? Too long ago, yeah, 2 years, yeah. 3 years ago. For me, it's actually more than 10 years ago, so yeah, a long time. Anyway, Ms. Guff, anything to say?
Can you do bottom up, slow down?
No, let's not worry about bottom up. We're going to look at that later, okay? The problem for this, basically, is about left recursion, okay? Basically, so let's talk about conclusion right away, and then we will show you. This particular algorithm, okay, for doing top-down, you can see this expression here, the recursion happens in the leftmost symbol right away. Agree? That's left recursion. Similarly, you got turn, also you got turn. Right? You got two occurrences of left recursion. If you got left recursion, you may just run into an infinite loop. But why? Let's see why. Okay? Let's try the following. Let's try to trace a little bit. Okay, you will get an idea. Okay? In order to trace it, let's get familiar with what we need. Okay? We're going to need, let's go line by line. Okay? First of all, we're going to create a root. So I'm going to create, for the start symbol, is going to be expression. Okay? Again, allow me to be lazy. E for this, T for this, and F for this. Okay? Let's say E here, start symbol, and then I'll make it a root of the tree. That one's easy. And then the focus is going to be the root. So I'm going to say the focus over here is going to be E. I'm going to have different colors for the nodes so you can see exactly what's happening here. And then we also got another stack, and the stack possibly will be long. So I will do it here. Okay, I can draw a little bit better. Okay, so that's the trace stack. and then initialize empty, and then we only push null. Okay? And then finally, we got word. So the word over here is going to be the first one, which will be A. Okay? That's the initial setup. Everybody okay with this? Okay. Maybe after the first or second iteration, you will see why you will run into an infinite loop. You will see very soon. So now, let's see which if branch we might satisfy. So now, what's the focus? Focus is basically E. Is E a variable? Yes, indeed. This guy here, right? It's a variable. So now we should go into this branch. So now, if you check this condition, you can see E produces either 1 or 2, right? 2 possibilities. We have not used any one of them, so we should use the first one. Let's say we go by the order. And now, I will do the following, okay? So now, let me say I put this as green. It's a record. Green here. So that means by applying this particular rule, I'm actually, and then I'm going to create a children's node and then set a children. Okay, I'll do all at once. I'm going to create one node for E and one node for T. And then we push every children except for the first one. So E will not be the focus. Okay, so now we only push T. T will be to the stack, and now the focus now is going to be the E. I can see the different color. You can see it's a different E. Right? So you can think about the focus is right now this particular node. Guys, are we okay? Okay. So now after this, that means we are at the end of this if branch. So we are done, and then basically we are done with this if branch, and then we're done for this iteration. Agree? Let's see what's going to happen next iteration. Go over again. Agree? Let's just do one more, just in case you haven't seen it. Okay? If we go for the next iteration, so currently the focus is E. So now we're going to go for this particular line. So now the focus is E. Of course, E is a variable. So we still check to see whether it exists on unvisited rule. So now you have to be a little bit careful. Okay? So now you can see previously, in order to generate this particular level, we already used the green. But now we're at a different level, so they don't count to be the same level. So you have to use, I gotta use a different color. That's why when you implement this algorithm, you gotta be a little bit more careful. Okay? So now, for this, as far as the green level is concerned, this particular line, this particular row is not considered as used, not negative. Okay? So what I will do is, I'm going to use a different color. I'll use pink. And then, so what I will do is, pink is going to help me generate, again, expression and also turn. And again, turn is going to be pushed, and then focus will be changed to E. So now you can see the process, right? Basically, if you keep going, E, T, and never ends. It got infinite loop. Coco, that's pretty good. That's what you're thinking about, I guess. Pretty good. Unless you change the order, but I would just say in general, if you got left recursion, then that's not good. Guys, are we okay with this example here? So the reason I show you something that doesn't work, first of all, is to see why. You can think about there's a precondition for this algorithm. You may want to run the require, like a precondition to say the grammar itself should not contain any left recursion. So we're going to see some systematic procedure later. Given the grammar, before you can apply that with the top-down parse algorithm, you have to eliminate all the left recursion and turn them into right recursion. That's something we'll see. Okay. Any questions? Okay. Yeah, I thought you have a question. Yes.
So there it says it exists unvisited, right?
Yeah.
Should we make sure that it matches the thing that we're trying to match?
So, okay. Over here, we are not matching anything just yet. Okay. Let me get you correctly. So which line are you talking about? This one here? Okay, what about it?
So it's matching the expression in the second time, but it's not supposed to because the expression is just a expression plus.
Oh, I see what you mean. Yes, eventually, apparently in this case, we have an infinite loop, so you will never get to have a mismatch. But later on, when we see another grammar which is equivalent but only got right recursion, you will see that we'll actually run into some bottleneck, like a mismatch, in which case we're going to backtrack.
Right.
That's what you will see.
But if you change the algorithm, this could as well work if you make sure that you're only matching the plus.
Yeah, so some later statement will actually handle that. Well, bear with me, we'll see that. Yeah. Yeah. Okay, so now I will suggest something. Okay. So today I need to finish the class a little bit earlier. I'll try to make up the time for you later. But let me just suggest something for you quickly. Okay. But the tracing a working code, working string is going to take a little bit of time, but I think it's worth doing to give you the insight. Okay. So guys, I would say for quiz number 2, you will cover only up to here. Okay? Study up to here. I'll give you the precise slide pages tonight or tomorrow morning. Okay? But please start studying, start preparing. And the only thing I want you to think about is this. Consider this particular grammar, which looks pretty weird. Long, maybe seems to be unnecessary. Okay, first of all, can you tell me if you agree there is no left recursion? Agree? For example, you can see over here, for this particular production over here, expression doesn't really produce the expression right away. So it's not left recursion, right? If you follow the same logic. Okay? This grammar here is so-called right recursive. And it's somehow this can be generated automatically in a systematic way. That's something also we'll talk about next week. Okay? So now, before next Monday, I would suggest some minor exercise for you to give a try. So that will also help you comprehend. So first of all, try to just go over the steps over here for the algorithm. I'll leave the empty page on the iPad for you. Okay? And then try to look at this particular one. This is something I'll do together with you on Monday. Okay? I basically put the left recursive version over here. I also put the right recursive version over here. You know how to draw the parse tree for this, for sure. Try to see if you can draw the parse tree for this. I can tell you that one takes a little bit more thinking. However, that one turns out to be exactly how the algorithm is going to produce. Okay, I would say do a little bit of preparation for Monday. Okay, any question for me? Yeah, question first, and then yeah. Oh, you came a little bit late. So we somehow we agree, or I said, we're gonna have since we got our first quiz on a Wednesday, so let's keep it consistent. So all the quizzes will always be on Wednesdays. I'm gonna announce that. And for your quiz number 1, I'll try to return back to you either Friday or Monday the latest. Okay, any other questions?
So wouldn't this one still run into an infinite loop because the XPR, the EXPR in the brackets is gonna loop back to the first EXPR?
No, it's okay because okay, we'll see more on Monday, but I'll mention to you briefly. You can see factor, first of all, produces just a brackets over here, so it's not really left recursive. And also expression over here is referring to expression here. That one there also does not have left recursion, so you will find.
But wouldn't, once we get to factor, the first one be EXPR, and that's going to back to the initial state?
No. So factor, if you go to, how about this? I'll prepare some example to show you on Monday. Okay, good. Okay, guys, we'll finish earlier today. Okay.